determine the pressure of, let's say, ammonia using the ideal gas law and van der Waals equation. Okay, where 1.24 moles of ammonia are in a flask that has a volume of 1.50 liters and temperature of, say, 25 degrees Celsius. And then for ammonia, the constants A is equal to 4.17 liters squared, atmosphere squared, per mole squared, and B for ammonia is equal to 0.0371 liters per mole. All right, so let's get started. Okay, let's do the ideal gas law first. Okay, so we're looking for the pressure. So pressure is equal to nRT over V. Okay, we have 1.24 moles of gas times R, 0.08206 liter atmosphere per mole Kelvin. The temperature at 25 degrees, 298.15 Kelvin. And all of this is going to be divided by 1.50 liters. So the pressure that we get is going to be in atmospheres. Pressure 8.5, 1.5 is something like 20.2. Okay, atmospheres. All right, so I'll put that right up here. The pressure ideal is equal to 20.2 atmospheres. All right. So now, let's take a look at doing this for real gases. Okay? And we know that, basically, this color pressure, okay, minus A squared N over V squared, no, A N squared A over V squared times V plus V minus NB is equal to nRT. Okay? So, I'm going to not put in the numbers here yet. I'm going to go ahead and fill in these numbers so I can calculate it out and divide it. So this is 1.50 liters minus 1.24 moles times 0.0371 liters per mole is equal to 1.24 moles times, go off the screen here, I'm going to put it right underneath, okay, is equal to, I'll put right here, 1.24 moles times 0.08206 liter atmosphere per mole Kelvin, okay, times my 298.15 Kelvin. Okay, you see that? Let's really just get out a little. Before. Oops. Let's just get this there. Okay, so now P plus n squared A over V squared, don't worry, I'll start putting in numbers there, is equal to this divided by that. So let's get those two values. 1.24 times 0.371, and you're going to subtract that from the 1.5, so I get something like 1.454. Don't worry, I know it's going to be 3 sixteenths liters is equal to, it's 1.24 times 0.0206 times 298.15. That gives me 30.34 moles cancel out, Kelvin cancels out, liter atmospheres. So P plus n squared A over V squared, okay, is going to be equal to 30.34 liter atmospheres divided by 1.454 liters, and that's going to be equal to 20.86 atmospheres. Okay, wait, we're not done yet. So let's go ahead and take this phrase here. All right, and I'm going right in the middle here, just to make sure I have enough space to work with. Okay, so what we have now is that my pressure plus n squared over A divided by V squared is equal to 20.86 atmospheres. So now let's put in the rest of the numbers and determine what the pressure is using the van der Waals equation for real gases. So the pressure is equal to 20.8, I'm going to subtract that, 86 atmospheres minus, and here's my whole phrase, 1.24 moles squared times A, 4.17 liters squared times atmospheres divided by mole squared. Okay? All of this is divided by V squared, 1.50 liters squared. Look at mole squareds divide out, liter squareds divide out, and then my answer will be in atmospheres, which is great. 1.24 squared times 4.17 divided by the square of 1.5. So I get 20.86 atmospheres minus 2.85 atmospheres. So my pressure using van der Waals equation for real gases is 18 atmospheres. Okay, so let's put that up and let's talk about, does this make sense? So using the van der Waals, the pressure is 18 atmospheres. Okay, So if you think about it, does that make sense? Well, we did say initially that because of the interactions between gas particles, that the pressure for a real gas can be lower or will be lower than the pressure of an ideal gas. Remember, we had the 10 particles, they didn't interact, so 10 particles hit the walls, whereas 10 particles, if they did interact, we had just a pictorial version, and it looked like 7 particles were hitting the wall. So what we find here then is that we are getting a decrease in our pressure. Now, why in particular do we see such a dramatic change?